I want you to take a moment and just look around this room. Look at the chair you're sitting on, the device in your hand, the frame of the building around us. Every single one of these objects began as an idea, a raw material, and was transformed. Today, we're going to pull back the curtain on that transformation. This presentation is based on a foundational taxonomy of manufacturing processes. Our goal is to build a mental framework, a map that helps us navigate the vast landscape of production, from raw materials to the finished goods that define our modern life. Let's start with why this matters. Manufacturing isn't just about smokestacks and assembly lines. It is the engine of civilization. It's the catalyst for human growth, the critical backbone of the global economy, and importantly, the largest consumer of our natural resources. Understanding this magic of making is fundamental to understanding our world. At its core, manufacturing is beautifully simple. It's a transformation system. Think of it as an equation. On one side, we have our inputs, raw materials, energy, information, and tools. The process of manufacturing applies these inputs to create our outputs, finished goods. And the key word here is value added. We are taking something in its raw, often low-value state, and through skill and technology, transforming it into something of high value. So, how do we actually perform this transformation? The world of manufacturing has hundreds, if not thousands, of unique techniques, but to understand them, we can distill them down to just 6 fundamental families based on their core physics. Let's walk through each one. First up is casting, the art of solidification. This is one of the oldest processes dating back thousands of years. The principle is simple. You liquefy a material, usually metal, by heating it until it melts. Then you pour that liquid into a mold that has a hollow cavity in the shape of your desired part. You let it cool and solidify, and then you eject or break the mold to reveal the finished piece. From the engine block in your car to a delicate piece of jewelry, casting is how we create complex shapes that would be difficult to carve or form. Next is forming. If casting is about liquefying, forming is about applying force. Here, we take a solid piece of material and reshape it by applying mechanical stresses, like compression from a hammer or tension from a pulling force. The key principle is the conservation of mass. We're not adding or removing material, just moving it. Think of a blacksmith forging a sword, or a massive press stamping out a car door from a flat sheet of steel. This family gives us structural beams, wires, and the body panels of almost every vehicle. Now we move to machining. This is the opposite of forming. Instead of moving material, we remove it. It's subtractive manufacturing. We start with a block of material larger than our final part and carve away the excess. This is the realm of high precision and tight tolerances. We have turning, where the workpiece spins on a lathe. Milling, where a rotating cutting tool shapes the part, drilling to create holes, and grinding for superfine surface finishes. And for ultra-hard materials, we have non-traditional methods like EDM, which uses electrical sparks to erode metal. This is how we make critical components for engines, transmissions, and precision tools. But what if your design is too complex to make as one piece? That's where joining comes in. This is the family of processes dedicated to unifying components into a single complex assembly. We can fuse materials together with welding, where we actually melt the base parts together. We can use adhesives with soldering and brazing, or we can use good old-fashioned mechanical force with rivets and screw fastening. Without joining, complex structures like aircraft fuselages or skyscrapers would be impossible to build. This image really drives the point home. On the left, we see subtractive machining. It's powerful and precise, but its geometry is limited by the tool's access to the material. On the right, additive manufacturing. It has incredible geometric freedom, but it's often limited by slower build speeds and a narrower range of materials. The choice isn't about which is better, but which is right for the job. Finally, we have finishing. This is all about surface engineering. After you've created the bulk shape of your part, finishing processes alter its skin to improve performance. The objectives are threefold. Protection, like anodizing aluminum or chrome plating steel to prevent corrosion. Aesthetics, painting a car or polishing a piece of jewelry. And precision, honing the inside of an engine cylinder for a perfect seal. It's the final touch that makes a product not just functional, but durable and beautiful. So, with 6 families and countless processes, how does an engineer choose? This is where strategy comes in. They use a decision matrix, weighing factors like the part's geometry, the required material, the needed tolerances, and most importantly, the production volume. The right process is the one that best balances these factors to create a successful product. The first major constraint is often the material itself. The material's physical properties dictate which processes are even possible. A highly ductile material like metal is perfect for forming. A material with high fusibility, like certain plastics or aluminum, is great for casting. But if a material is extremely hard, like titanium or hardened steel, your only option for precise shaping might be machining, and you'll need some very tough tools to do it. And then there's the economics of volume. This chart is crucial. Processes like die casting or injection molding have high upfront costs for tooling, but a very low cost per part. This makes them economical at high volumes. On the other hand, 3D printing has almost no tooling costs, but a higher cost per part, making it perfect for low volumes and prototypes. The break-even point tells you which process is most profitable for your production run. But where do we go from here? The frontier of manufacturing is at the microscopic and even molecular scale. MEMS, or microelectromechanical systems, allows us to manufacture microscopic gears and sensors, the brains inside your smartphone's accelerometer. And nanotechnology is about manipulating matter at the molecular scale to create new materials with incredible properties. This, combined with electronics manufacturing, is how we integrate these tiny scales to build the computers and devices that power our world. All of these advances are converging in what we call the digital factory, or Industry 4.0. This isn't just about automating a single machine. It's about connecting the entire supply chain. We're seeing a world of robotics providing autonomous efficiency, connected supply chains using data to optimize logistics in real time, and tool-less production, where industrial 3D printing starts to replace massive warehouses of spare parts. The factory of the future is flexible, intelligent, and data-driven. Which brings us back to where we started. By understanding these 6 families, casting, forming, machining, joining, additive, and finishing, we gain the confidence to see the world not just as a collection of objects, but as a landscape of possibilities. We gain the ability to select, to plan, and to create. It's the fundamental engine of our civilization, and now you have the map to its architecture.